Alrighty, nerds, we're going to go ahead and finish up the lesson that we didn't quite get a chance to finish on Friday. And then we're going to do the addendum notes, which is just me adding a little bit onto the end of today's notes because I need you to really fully, deeply understand the concept. Let's go ahead and tackle this one first because we did start this one. What we did was we put these numbers through the paces of first differences, second differences, and third differences. And what we found was that once we did the third differences, we got the exact same number every time. So because our third differences was a constant value, it tells us that we're dealing with a cubic. If our second differences are the same value every single time, where it's quadratic, if you have to go all the way to fourth differences, it's quartic or fourth degree polynomial, so on and so forth. Don't worry, I'm never going to make you go past the fourth, because our calculator can't go past the fourth. It only goes up to the fourth regression and doesn't do anything after that. Probably because that's just ridiculous. But anyway, I wanted to get the actual equation for this just so we could say that we saw it happen in the notes. Actually, so I'm going to go into my... yes. Okay, so I already have mine filled out from earlier, but we just put them in. And you don't have to go through this with me. I just need you to see it because we already know how to put things into a table. I just need you to see where cubic regression is. It's the same place that linear and quadratic regression is. Stat, calc. Cubic regression is that one. And then it goes to quart regression, which is fourth degree, and then it starts doing stuff that we'll be doing at later points in time. So I say yes, cubic regression. I'm not going to do anything with it, so you guys don't have to have this equation right now. And I'm just going to hit calculate, and it gives me the equation. But what I do want to point out to you is what is going on with the coefficient for b, meaning the number that sits in front of x squared. Remember that this calculator is not doing a lot of the mathematics like we would have done it by hand. It's doing very complex estimations. And because of that, it'll occasionally give us ridiculous answers like this. This is 1.5 times 10 to the negative 12. It's scientific notation. It's literally 0 point and then 11 zeros and a 1.5. What that means is b is 0. It just couldn't say it, but b is 0. Okay? So our cubic equation, our cubic polynomial is f of x equals... And even though it gives you its coefficients as decimals, I would give you those numbers as fractions on a test. So I would hope that you could convert them to fractions. Luckily, you'll have a calculator in hand if you need to. But 0.2 is 1/5. There is no b term. That's the closest thing the calculator could get to 0. C is negative 7/10. And D, 2.9, 2 and 9/10, that's 29 over 10. So you got that r squared. 1. It's perfect regression. What that means is, actually I had the equation before I had the table. I used the equation to create the table. That's what that means. No, b is 0. b is 0. It just couldn't say it. It gave you 0 point, and I'm like 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1.15. Essentially 0.
But if we got that on a test?
It would be 0 on a test. It's like when you do your second trace intersects and it tells you they intersect at 2.999999. No, that's 3. That was just the best it could do. Okay. Adi?
You have to write the fractions on the test, right?
Yes. Fractions, please. Because I don't know how AP would grade something like this. So for now, let's just say yes with fractions. Okay? And the last piece of Friday's notes, designing a box. We've done this before. A company was contracted to make boxes out of a piece of cardboard. You know, they're going to cut corners off and they're going to fold up the sides. When we did this question last time, we maximized the volume. This time, the company has very specific directions. No. The volume has to be exactly 484 cubic inches. We need to figure out what size squares to cut off the edge of our box. Or I guess to say to cut off the edge of our cardboard. And you know what? I actually happen to have a brown colored pencil with me right now, so I'm going to draw this in brown. Because, why not? It's cardboard, right? Then we got a machine that's going to come by and it's going to stamp some squares off of the sides. What size squares? We don't know. So we'll call them X. What we do know is that originally the piece of cardboard was 20 inches by 25 inches. Before we cut pieces of it off, right? And again, because I happen to have a brown colored pencil on my table today, here's my box once it has been folded up. Rectangle. Parallelogram on top. Parallelogram on the right. And a vertical line showing me the inside of the box. There it is. There is my box. So this thing was 25, but then I stamped a couple of squares off. So how wide is it going to be right here? What are we going to put here now that I've stamped off these X's? What do you got for me? 25 minus 2x. Ooh, looks like I smeared some. Oh no, it's getting worse. This length was 20, and when I stamped its couple of x's off, the same trick is going to happen. So 20 minus x, and this height of the box is actually what's going to happen when this and this flap come together. So that's where these two numbers touch. That is x. The volume of a box, oh, I forgot the 2. The volume of the box, all boxes, is length times width times height. And we actually have something to put in all 4 places. Yes, ma'am. What's up?
How do we know the height is X again?
So the height of the box, this edge right here, is going to be what's created when this flap and this flap touch. So if you can imagine, that's the bottom of the box, is what you see in black. This is a side flap, and this is a side flap. And when they come up and touch, those 2 red lines become one line right there. Cool? Okay. We know something for all 4 of those. The volume is 484. But it's also length times width times height. X times 20 minus 2x times 25 minus 2x. Now before I go using my calculator for anything, we need to talk about the domain restrictions. This is a real object. So what do we know about the number x? It can't be 0. Good, Ashley. And so it's got a smallest value. We know that x needs to be greater than 0, but it does have to be less than something. Less than 10. Because this is going to be the smaller of the 2 lengths. And we have to make sure that it's not a negative number. So you say 20 minus 2x better be greater than 0, and you solve for x. So you say 20 minus 2x better be greater than 0. Solve for x. You get x is greater than 10. Less than 10. Oh, crud. Yes. Wow. It looks like crap. There. So we could hate ourselves, distribute all this polynomial out and set it equal to 0 and try to solve by hand. Or we could thank our lucky stars that we know how to use some technology. Because what we could do is we could call this expression y1 in our graphing calculator, and we can call the number 484 y2 in our graphing calculator, and we can just ask it to find the intersection points. Yes, Paul. You set this thing greater than or equal to 0, subtract 20, and you'll get negative 2x greater than negative 20, divide by negative 2, and just remember that when you divide by a negative, it flips the inequality over. You mean, why didn't I use 25 minus 2x? Because if you set this equal to 0, it's going to allow x to be all the way up to the number 12.5. But if you try to put 12.5 in there, you're going to get that this side length is negative 4.5 or something like that. So you had to go with the smaller of the two sides because it's the restrictive side, and just make sure that it's a positive number. We're going to graph those and do second trace intersect. And I'm pretty sure, oh, I didn't have it in there. X and then parentheses 20 minus 2x and parentheses 25 minus 2x and then 484. Now let's talk about our window. Before we hit graph, let's talk about our window. We already know that the domain, the x values, are going to go from 0 to 10, yes? The y values are actually our volumes. Negative volume is not possible, and we're trying to see where the number 484 crosses. So I'd say that's roughly half of the number 1000. I just like my answers to land in the middle of my screen. So I'd go to my window, and I would say 0 to, what did we say, 10? And my y minimum, 0. My y maximum, is already at 1000. Okay. And then just divide by 10. You'll get 10 tick marks. And hit graph. Whee! Get this pretty curve. We're not maximizing this time. We're specifically looking for which x values will get us that specific volume. And it looks to me like there's 2 of them. So we do second trace intersect and find them both. Second trace intersect. Intersect is number 5. Yes, yes, and I'm going to scroll left. And hit enter. We have an intersection at x equals 1.222 inches. Remember your units so you don't lose any marks on the free response, because there's a question like this on the free response. It's the extra credit question. And we have to find the other one, second trace intersect 5 again. So yes, yes, scroll. I guess I didn't have to scroll. I could have typed the number it's close to and hit enter, but whatever. Yeah, you can do that. 6.871. So as long as you cut off little squares of either this size or this size, you will have a box with a volume of 484 cubic inches. Yes, Adi. It's both. It's there because they both work.
So if you write only one, would you still get it wrong?
If you write one, you would get half the. So the way it's going to be graded is I'm going to grade it like an IB mark scheme. So the final answer is worth 2 points because each one of these is its own answer. Alrighty? Okay, now let's work on the addendum notes. This is being added to section 2.3 because I felt like it was necessary. This doesn't have its own homework assignment. It's just to reinforce the skills that we've learned so far. And I'm really trying to tie everything together for you. Here I have an equation, some cubic, that I created. There's its graph. Just by looking at the graph, we should be able to see where it's increasing, decreasing, concave up, and concave down. Remember, increasing, decreasing gets brackets when it changes. Concavity does not. You guys are going to be reading these graphs from left to right, riding them like a roller coaster. Okay, chilling. So from the left, we're going up. I'm sure you could see that. But at what x value do we stop increasing? At x equals 1. At x equals 1, we stop increasing, and that's where we fall. We are now decreasing from x equals 1 to when? When do we stop decreasing? At x equals 5. Good. Because at x equals 5, we begin increasing again and never stop increasing after that. Good old chapter 1 stuff. What about concavity? Do you guys remember how to find the place where concavity switches? How we estimate it? When you say the middle, what do you mean the middle of what? Between, there it is. Between two extreme values. So between these two x's, because we have an extreme value at one of them and an extreme value at a maximum here and a minimum there, you go halfway between a maximum and a minimum, and that is how we will estimate where we find our change in concavity. That point would be 3. So halfway between 1 and 5, the average of the numbers 1 and 5 is 3. This is your inflection point. So, which side is concave up, left or right of that point? Yeah, which side is concave up, left or right of that? To the right. So we are concave up to the right of x equals 3. We always use parentheses for concavity. And we're concave down to the left of the number 3. Like you said, good old algebra, not algebra 1, chapter 1. Are you comfortable with those ideas? Yes? Okay. Here's what we are going to do. We are going to take this equation and we're going to use it to fill out this table for its y values. And we could do that a hard way by plugging every one of those, it's like 10 or 11 numbers, into the equation. Or we could let the technology do that for us. So we're going to go back to our graphing calculators, go to y equals, clear out what you have in there, and instead type this equation. So I'm back to y equals, and I typed it in. Good? Our graphing calculator can tell us what the y values are at any x value. And it could do it as a list, but not like a stats list. It'll do it as a table right there. So press second graph, and it's going to bring you to a table like this. You can scroll up and down if you need to see more x values, and you can see that it gives you the y values that correspond with them. So go ahead and take the time to fill out the table that's on your paper with the y values that are right there. There. Now, something I didn't teach second period, and that was because I decided I didn't want to, but actually, let's do this by hand, and then I'll show you the calculator trick. All right? So we are going to figure out what is our first differences, and that's what this is. This delta sub 1, delta 1y, that's first differences. Delta 2y is second differences. That's all that is. So first differences, I'm going to figure out what did I have to add to the number 128 to get, with negative 128 to get negative 49. And I believe it's 79. Negative 128 plus 79. Yes, it's plus 79. And I'm going to put a plus. And then here I've got a plus 49. And you see I'm putting it between the two numbers. That's why there's no lines. Microsoft Word's table feature was not being very kind to me right there. it wouldn't let me split this into a different number of rows than what I had here unless I was going to do it in even values. So it wouldn't let me do it. It complained. So I just said, fine, I won't use it then. Then plus 25, then plus 7. Oh, then minus 5, minus 11, minus 11, minus 5. Then plus 7, plus 25. Very interesting. Very interesting. Alrighty. Now let's do our second differences. To go from 79 to 49, I had to subtract 30. To go from 49 to 25, I have to subtract 24. Then it's minus 18, minus 12, minus 6. Goodness. Oh, but to go from negative 11 to negative 11 is just nothing. I'm not going to write plus. I'm just going to write 0. And then to go from negative 11 to negative 5 is plus 6, and then plus 12, and then plus 18. So neat. Now that you've seen how to do it by hand, in case you didn't know how to add and subtract, your calculator can do this also. Would you like to see? I didn't show this to period 2. Go back to, you know you have this as y equals, right? So this is your y1, yes? Here's what you're going to do. Stat, edit, stat, edit. I'm going to clear these lists. Clear, enter, clear, enter. These are lists, okay? So check this out. I'm going to come up here to L1, and I'm going to hit enter. Oh, I guess I didn't have to hit enter. I want it to show me y1's values. Vars, yvars, function, y1, enter. Uh-oh, data type, it didn't like it. It doesn't like it. Go to. Huh? No, it didn't let you do it. It didn't fail yet. What, yours worked and mine didn't? Is that what you're saying? Where did you put the y1? No, did you put it? Okay, I don't think she understands what I'm asking. Oh, okay. See, man. All right, tell you what. I'll figure that out at another point in time because right now I don't want to have to put all those in by hand, and I know there's a way to do it. I just can't remember how. Let me try one more thing. I'll have to do it at another point in time. It wasn't necessary, but I'll show you at another point in time. Well, if we could have gotten it to show us these y values, there's a command that we can put in that'll give us those and those. The only problem is, you see how I've done it so that they taper down like this? The calculator's table can't do that, so it has them lined up horizontally, which really is confusing to me because I needed to see when very specific things were occurring. My directions that I type say, compare these delta 1 y values from this table to the increasing, decreasing intervals from up here. Tell me what you notice. Look at these increasing, decreasing intervals, and then look at my numbers in green, and tell me what you notice. At what point did it stop going down? 0. These numbers are positive. Hey, what the hell is happening back there?
When he puts in Y1, it just puts 275 first box. That's it.
What I was trying to get you to see is that if you look at all of the x values from negative infinity up to positive 1, your delta 1s are positive. And then if you look from 1 to 5, your delta 1s are negative. And then after 5, your delta 1s are positive again. As it turns out, anytime delta 1 is positive, anytime your first difference is positive, your function is increasing. First difference positive implies function is increasing. So first difference negative implies function decreasing. Now, look at your concavity intervals and look at delta 2. Do you see how they compare? What about concave down? So when delta 2 was negative, when your second difference was negative, the graph was concave down. And when your second difference is positive, the graph is concave up. I'm going to say it the other way around. So second difference positive implies concave up. Second difference negative, whoops. Implies concave down. That means just by looking at this table, we can see where the inflection point occurred. It occurred right here at x equals 3. So I'm going to get really technical here. Is it because the second difference is 0? No. It's because the second difference changed from negative to positive at x equals 3. And of course, you can't change between positive and negative without passing through a 0. But a 0 doesn't guarantee an inflection point. Inflection points occur when the second difference changes symbol. Yes?
Is that what you were talking about when you said like it's complicated to find like the intersection point or whatever?
The inflection point? Yeah, and actually even this way is only it's kind of like a trick that only works if you have your x's progressing nicely. Because if the x's didn't go like that, if I didn't have an equation, then I wouldn't have been able to use first and second differences. And at that point, like again, we're just forced to estimate by taking an average. So let's fill out this bottom table, and I'm actually going to write a little bit more underneath it as well. I'm not really sure if it's necessary for you to have this level of understanding for AP Pre-Calc or not, but it is necessary for AP Calculus, so you might as well learn it now. First of all, when are functions increasing? Functions are increasing when the first difference is positive. Therefore, functions are decreasing when first difference is negative. Before I write down stuff for concavity then, I want you to understand something very special happens every time you see the first difference change symbol. Right here it changed symbol at x equals 1, didn't it? And what was going on at x equals 1? Look up at your picture. What was going on at x equals 1? It's an extreme value. And then look down here where it changed again. At x equals 5, it changed symbol again. Extreme values are found when our first difference changes symbol. So they're extreme when the symbol changes between positive and negative and positive. Going up to down, maximum. Going down to up, minimum. Concavity. Function concave up when the second difference, that's ascend. Second difference, positive. And they're concave down when the second difference is negative. So guess what I'm about to write next to that? Inflection points when symbol changes. I don't know. I said I was going to write that underneath the box, but let's get it inside the box. That's what I did here. I don't know if this blue and purple fact are necessary for your level of understanding in AP Pre-Calc, but it is necessary for AP Calculus because that rule will not change in AP Calculus. They just won't be called first and second differences. They'll be more specific. They'll be called first and second derivatives, but it's the exact same concept. And that ends the addendum, nerds.